So today we're going to talk about changes in populations and more about those growth patterns that we see. So remember we showed you this equation last time. This is how you calculate the percentage growth rate for a population. You look at the birth rate and the death rate, get the difference between the two, and you also look at immigration and emigration to see how the population is changing. And that will give you the percentage growth rate for a given period of time. Now that period of time is going to vary. It's going to be based on whatever period of time you collected this information for. So let's do an example to show you how you'd use this. So if you start with a population of 10,000 individuals, then you have 100 births that occur. So basically we want to put that in terms of how many people per thousand. So that's 10 per thousand births. 10 births per thousand people, 50 deaths, that's 5 per thousand people, 10 immigrants, that's 1 per thousand people, and 100 emigrants, 10 per thousand people in a given year. So we're going to take this and we're going to use this to calculate our growth. So basically here we have our growth rate, which is going to be equal to the number of births. So let's use this fraction here. So this is 10 per every 1,000 individuals minus our number of deaths, which is 5 per every 1,000 individuals, and that is our first part of our equation. Then let's add in, alright, we have 1 immigrant per every 1,000 individuals, and that also means that we have 10 emigrants per every 1,000, according to our information up above. Alright, so if we do it that way, then we can take it at that point and we can turn these into decimals. So that gives us 0.01 here minus 0.005. Alright, so take that and these fractions over here work out to be 0.001 minus 0.010. Alright, so once we have it in this decimal form, the math becomes much simpler. If you subtract this here, you will get 0.005, and then we add that and we subtract over here, and we get 0.009. And when you do this math out at the end here, you're going to wind up with a number of negative 0.004. Or, in other words, what this means is we're going to multiply this by 100 to get our percentage growth rate, which is negative 0.4%. And for this particular example, this is talking about a given year, so this is per year. Alright, so what this is telling us is that the population is decreasing by this percentage every single year. So every year that goes by with these particular rates, this population is going to continue to decline. Now in this example, this was already talking about just 1 year. But in some cases, that's not going to be the case. You're not going to be talking about an annual rate. So you will want to find an annual percentage growth rate, or how much it's growing every year. So basically, if you have a population that grew 12% in size over a period of 10 years, it's pretty easy to get the annual percentage growth rate, because all you're going to do is take that 12% and you are basically dividing it by the number of years that it took in order to get there, and of course when we do that we get 1.2% per year. So annual growth rate again is just how much is it changing per year, and sometimes that R value will be already per year, sometimes it won't, so you have to be careful. So there's another rule here called the rule of 70, which has to do with doubling time. So doubling time is what it sounds like. It's how long it takes for the population to double. So we can figure this out if we know the annual percentage growth rate, that growth rate per year. So you can basically do this by figuring out, by taking this number 70 and dividing it by that annual percentage growth rate, that R value, and that'll give you the amount of time it's going to take for your population to double. So in our example here, if our population is growing 10% annually, that's telling us it's already per year. All right, it's growing 10% per year. We're going to use our rule of 70, and we're going to take 70 and just divide it by our 10%, and that is going to basically tell us the doubling time. So if you go ahead and do that, of course, 70 divided by 10 gives us 7. So what that's telling us is it's going to take 7 years for this population to double in size if it keeps growing at this 10% annual growth rate. All right, so if your population doubles every 5 years, what you can also tell from this is you can use the same equation to get back to what that annual growth rate is. So if you do some algebra here, you'll notice that if we take this equation and we start off here with doubling time equal to 70 divided by r, you're going to have to multiply both sides by r and then divide both sides by doubling time in order to get r on its own. So basically our new equation at that point would be r equals 70 divided by the doubling time. I'm just going to use dt for that. All right, so if we know that our population is doubling every 5 years, what we can do then is solve for r by taking 70 and dividing it by 5. And that, of course, gives us an annual percentage growth rate of 14% per year. So since we knew the doubling time here, we can use this rule of 70 in this case to get back to that R value, that annual growth rate. Now there's another type of calculation you should be familiar with. It's also very logical. It's called population percent change. And basically you just want to see the difference in your population and how, by what percent it has changed over a certain period of time. So if you look at the equation here, you're going to take the ending population and subtract the starting population from that, and then you're going to put that over the starting population and multiply by 100 to get your percent population change. So for instance, in this example, in 1980, if the city had 250,000 people, and 1990 it had grown to 280,000 people, we want to find out the population percent change. So our ending population here is our bigger one. So we know that in the end, we had 280,000 people, and we're going to subtract our starting population from that, so that's 250,000 people, and then we're going to put that all over our starting population of 250,000, and eventually we're going to multiply by 100. So you can go ahead and plug that into a calculator, and go ahead and pause here and do that. And if you calculated this correctly, you should wind up with a population percent change of 12%. So that's the percent that the population has changed over this period, in this case of 10 years. Right. So remember, any of these changes, and usually we talk about this in terms of growth, but it could be a decline in population too. It depends on these things here. The age structure of the population, remember from last time we said the younger the population, the faster it's going to grow. The population's biotic potential, remember that's like the biggest size it can possibly be, and the fastest growth rate it can possibly have is called the intrinsic growth rate, and that's based on what's available in the environment, how fast the species reproduces, that kind of thing. And then growth also depends on the amount of environmental resistance. So there are a lot of limiting factors that are limiting this population. Is it near its carrying capacity or over its carrying capacity? Because that's going to limit its growth. So remember that populations tend to show exponential growth until they meet that environmental resistance, until those limiting factors start to really take hold and they start to reach that carrying capacity, and then at that point they're going to switch over to more of a logistic growth pattern. All right, now there's 3 types of what we call survivorship curves, which are basically looking at how many organisms are alive at different stages in their life. So this word survivorship basically means the proportion of individuals that are still surviving at that age. And there's 3 types. Type 1 is called the late loss type. it's when the species tend to die late in their life. So we are type 1 individuals. We die as we get older and we're in old age. These tend to be K-strategist organisms as well. Type 2 is not as common. It's a constant loss. These types of organisms, their death rates are the same pretty much no matter what age they are. So songbirds actually experience this. There aren't too many examples of this type 2 survivorship. And then type 3 is an early loss where they're much more likely to die as babies usually or earlier in their lifespans before they reach reproductive age. So things like fish and amphibians, reptiles, they lay lots of eggs. They're usually R strategists because they die early. So these survivorship patterns are part of what's going to influence these growth rates that we see also. Now there's another thing called metapopulations, which is basically a group of local populations that's close enough to each other that they can disperse amongst each other. And what we mean by that is they can migrate, they can emigrate from one habitat to another. So these are called metapopulations because they're all sort of connected. They can all travel through these corridors to get to each other. And when you have a metapopulation, you wind up with what we call source and sink habitats. So pause here for a second, write down some characteristics here of these source habitats and sink habitats. So basically, these source habitats are the better habitats, and that's where you're going to get most of your population. But because you have such a high population, you're going to have more competition, so sometimes organisms will leave to find other habitats. If they leave and they find an area that has less favorable conditions, then they're probably going to have higher death rates than they have birth rates, and that population is going to slowly decline until they become extinct, and that would be called a sink habitat. All right, so we don't want to have lots of sink habitats, but unfortunately as we fragment habitats even more and break them up and remove those corridors, we get even more sink habitats as well. Naturally, populations tend to change in certain patterns. So there's 4 ways they can change. The first one is just irregular changes. These are kind of due to chance. There's a natural disaster. Something came along. This is not a normal pattern. And then let's talk about each of these next 3. So the first one is called a stable or non-fluctuating pattern, where basically you're staying very close to carrying capacity. You might be changing a little bit because of those limiting factors, but you're not changing very much. You're staying very close to carrying capacity. And a lot of times you will see this with populations of prey and predators where they kind of follow each other in this stable pattern because the prey are going to determine the amount of predators that can survive there. So we've seen this before with the snowshoe hare and the lynx. Lots of different situations follow this pattern. Another pattern is a cyclic pattern. This is when you have regular, predictable ups and downs. This is also called a boom and bust pattern because the population starts doing really well and then it will start to crash. So the 7-year cicada that comes out every 7 years, that would be an example, and then it dies off and then it comes back again. This is another example here. This is a population of lemmings, and as the population is increasing in these number 1 scenarios, the density-dependent limiting factors are becoming more and more severe until the population crashes, and that's happening in number 2. But as it crashes, the density-dependent factors start to relax because you don't have a big population size, and then the lemming population goes up again. Just kind of an aside, lemmings do not actually commit mass suicide. That's a common myth, so it's good to set yourself straight with that. Another population pattern is called an eruptive pattern, and pay attention to the spelling here because it's commonly misspelled. So in an eruptive pattern, the populations explode all of a sudden, and then they crash down to a more stable level that's right around their carrying capacity. So again, you have recurring ups and downs, but this time it is unpredictable. It's not a fixed pattern. You have these really high population densities, and then all of a sudden it crashes. So this is most likely to happen right when the population first inhabits an area, or if the predators are taken away and the weather and the food supplies are all in the species' favor, then it will jump up for a while, but eventually it crashes down to carrying capacity. So actually lately we've seen this happen with snowy owl populations in the US, and we've seen the snowy owls basically come down into areas they're not usually found and also go through a big population growth. And there turns turns out to be a lot of reasons behind this, and they're still trying to figure out some of them. But basically, the conditions are so good at a certain period of time that the population explodes. So that's our last type of pattern. Right, so come in ready next class to talk about these different patterns and these different changes that these populations can undergo.